Yay!
Are we still gonna have like one more take-home test?
Yes, I'm gonna post it Thursday.
Final?
I'll post a take-home test on Thursday. It'll have the nuclear chemistry stuff on it, and what we're about to go into, which is oxidation reduction equations and balancing. Yes, I'm rolling my eyes because I think it's, well, anyway, it's just my opinion. Doing oxidation reduction reactions, and that's what it'll be. A fairly straightforward test. It'll be due Tuesday. Post it Thursday, it'll be due Tuesday. Then we won't have lab, we'll just have makeup day, whatever. And I said we'd start our final in here Monday? No, the next Wednesday. So we'll have a couple days for review, a couple days, well, that day to go over the test, give it back to you on Monday, go over the test, review on Tuesday, start the final on Wednesday.
2 weeks from this one.
So the final is from everything we learned past the midterm?
Nope, final's everything.
You sure you can't make it everything we learned?
Nope. It's gonna be everything. What? Dun, 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 dun. Well, but we can go over and make sure, you know, I'll have a copy of the final ahead of time. I'm gonna write it, but I'll have a copy, we'll have it in the final. But a copy of the final ahead of time, and we'll go over and make sure, because I know I think y'all were kind of struggling with not pH calculations per se, but more the concentration and the KSP and
the hydronium
the hydronium ion and all that. So we'll go over that again before the final. Okay. All right. I have to take that and go get blessing on us going to the watch poo when the day. Okay. Any questions on the nuclear energy stuff? Pretty straightforward with balancing equations. The two sides just have to add up. I don't know if anybody's interested. I've already got us a room for Sunday, 1:30 to 6 at the library. All right. Oh, any questions from the movie?
Is it called the Manhattan Project on Netflix in 1986? I wasn't sure.
No, it's called Day One.
Day One. Some other movie. I was about to watch it, but I didn't think it was the right one.
Yeah, I mean, there are a lot of movies about it, but Day One, as far as the people who are involved in the development of this, they say it is the most historically accurate to what actually happened and what they were put through. A lot of them, what it doesn't show is how many of them were coerced into joining the project. I mean, basically, if Groves wanted you, you had no choice. He made sure that the Army made your life miserable if you didn't come, including threatening and pounding your family.
Very American.
Yes, the U.S. was hell-bent on making sure that we beat everybody else to this thing, and we did whatever it was decided they needed to do. Including, you guys do know that, like in World War II, anybody that was of Asian were put in imprisonment camps. Yeah. All right, oxidation reduction reactions. You can't have one without the other. Oxidation is considered the loss of electrons. Reduction is the gain of electrons. Okay. And there are a couple of different mnemonic devices to say Leo says GER Leo, loss electrons, oxidation, Ger, gain electrons, reduction. Or there's another one that's called oil rig, which is the one your book uses. Oxidation is loss, reduction is gain. Okay. And if you think about it, when you gain electrons, you're actually reducing your number. And what you mean by number is your oxidation number. For most things, your oxidation number is the same as the charge. So everything in group 1 has a +1 charge, so therefore its oxidation number is +1. So on and so on and so on. There are certain rules though, they're weird rules. Okay. And if you look at page 490, there's rules for assigning the oxidation number. For instance, if I've got, let's say calcium oxide. It's pretty straightforward. Calcium is in group 1, and if you look at the rule number 4, in compounds, the oxidation number of group 1A elements is +1. So calcium is +1, that's your oxidation number. If you look at rule number 6, in compounds, the oxidation number of oxygen is usually -2. Calcium's in +1 or +2? Calcium's in +2. Okay, so there are your oxidation numbers for calcium oxide. Happens to be the same thing as if you were doing its charges. It was combining with somebody. The funkiness kind of occurs when you've got polyatomic ions or you've got things by themselves. Okay? For instance, if we were going to calculate the oxidation numbers for each one of those compounds, or each one of those parts of the compound, the total compound needs to be 0. Just like when you calculate the charges. Unless you're a polyatomic ion and you've got your own particular charge. Your oxidation number total has to match that charge. Okay. So if we look at this, oxygen we know is a -2. So how much do I have on that end?
Times 3.
Times 3. So this is going to be -6. Hydrogen we know is a +1. In this case, we've got to equal 0. So what does the chlorine, if you notice chlorine, it doesn't usually really talk about a rule with a halogen.
So then what that means, well, we have to do a +5.
So in this case, the oxidation number for chlorine is a +5. So in that case, it doesn't really match its charge. That's its oxidation number. If I've got something like SO4, it's a polyatomic, and it's got an overall charge of -2. So its oxidation numbers have to equal or balance each other out to be -2. Oxygen, again, is -2 on its own, and I've got 4 of those, so that's -8. So therefore, the oxidation state, or the oxidation number for sulfur, has to be +6 to equal the -2 charge that the polyatomic ion has in and of itself. Okay with that?
How did we know that the
Because rule number 6 says, in compounds, the oxidation number of oxygen is usually -2, except OF2.
No, I meant, how did we know it, the polyatomic charge?
Oh, that's on page 1 170. Every polyatomic ion has its own unique charge. So, we're going to the Waterworks' lab on Wednesday. I'm gonna watch them turn poop into energy. Alright, so then what if I took, sulfite, which is SO3, but it also, as a polyatomic, has a -2 charge. So in this case, the oxygen.
In all the cases, will have to match with the oxygen?
Because the oxygen has a specific rule about it. The others, right? So, oxygen is always -2. I've got 3 of those. So on this side, I have a -6 charge. So what does the oxidation state of that sulfur have to be? 4. Plus 4. So that's how we calculate the oxidation numbers of individual compounds. Okay. We've got 2 things in there that have rules about them all the time. We've got hydrogen and oxygen. So oxygen is a -2. Hydrogen is a +1, and I've got 2 of those.
+2.
So what's the charge of my carbon? Or the oxidation number, rather, of my carbon?
0.
0. Yeah, it's already. Okay. What's the oxidation number for each element?
-2.
That's gonna.
-8 for
H is gonna be
oxygen.
negative, not negative, but positive 3.
+3 for the H.
And that's gonna be -8.
-8. So the oxidation state for the phosphorus has to be
Positive.
+5. But then if I had so oxygen is -8. So this has got to be +7 to have a total of a -1 charge. Not so bad. Have you done this before, chemistry?
I remember going over the rules. We pumped them in our head.
Have I had anything you haven't done?
I guess he taught Chem 1 and Chem 2. I was wondering why it was so hard.
Okay. Where this really comes into play is when we've got oxidation reduction reactions. For instance, in Chem 1, did we do it in here too? We did a lab where we took aluminum and copper 2 chloride, and we ran an actual oxidation reduction reaction, which also looks like a single replacement reaction, where the silver and the copper actually traded places. So we had a beaker, and we had the copper chloride in here, and it's a blue solution. It's a very pretty robin's egg blue. We took a piece of aluminum foil, crumpled it up, and dropped it in here. The reaction was spontaneous, generated a buttload of heat. I think some of them heated up like 40, 50 degrees even. And what happened is, where the aluminum foil was, the metal ions were replaced with the copper in the solution of the copper 2 chloride. So you saw the foil disappear, you saw the blue color out of here disappear. This turned more gray, and then you developed copper, where the aluminum was. That is a very standard oxidation reduction reaction. The metal ions taking place of each other. When we ran it, we then ended up with aluminum chloride plus Cu. Now, who was oxidized, who was reduced? When you've got items by themselves, whether they're a monatomic element or a diatomic element, if they are by themselves, they have a charge of 0. Here, the chlorine is a -1. I've got 2 of those for a -2. So the copper's got to be a +2 oxidation state. And chlorine is -1. Here the aluminum is a +3, and this is going to be a -1. And the copper is by itself, so it has an oxidation number of 0. So if we look at the aluminum, aluminum has gone from an oxidation state of 0 to a +3. We have increased, we see an increase in oxidation number. So what has aluminum had to do? If we're increasing the oxidation number,
Reduction. Is that a reduction?
it's gotten rid of electrons.
Okay.
Or lost electrons. And if Leo says GER, loss of electrons is oxidation. If we look at the copper, it goes from a +2 to a 0. So it's a decrease in oxidation number. So it's gained electrons. And it's been reduced. What about the chloride, or the chlorine? Stay the same, so we don't even worry about it at this point. So, what does all that mean?
Just tell you what happened.
Just telling you what happened. And to make things a little more confusing, whatever undergoes oxidation is called the reducing agent. And whatever is reduced is the oxidizing agent. That's my ox.
What was the first one? Whatever goes through what?
If it's been oxidized, it's the reducing agent. If it's been reduced, it's the oxidizing agent. So let's spell that right. Okay. Now, theoretically, we can balance these equations with these numbers. Of course, we can also balance these equations just by looking at them. I don't really know why, although sometimes you can get half numbers, but we won't even really go in here. You can sometimes have coefficients of half or a fraction. All right, so let's kind of look at this and say, if I were to look at this equation, this I've changed by 3 and this I've changed by 2. So what's the common denominator kind of sort of there? Of 3 and 2. Basically the same thing we do when we're balancing regular equations. So this is going to be changed by 6, right? If I look at the common denominator. So to balance the equation, I would need to do this, 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 and this. Copper went through a change of 2, but in order to get it to match the same change that aluminum went through, we're going to need to multiply it by 3, and vice versa. Okay. Let's do another one of those. And to be honest, when I'm balancing equations, very seldom have I ever resorted to using oxidation reduction. Normally, just balance them. But this is just another way of doing it. So, let's look at this one. Okay, so the first thing we need to do is assign oxidation numbers. So oxygen we know is always going to be a -2 unless it's combined with a fluorine. So that makes the lead +2. Oxygen's -2, so this time carbon's +2. Lead's by itself here, so it's 0. Oxygen is -2 times 2 is -4. So the carbon's got to be +4 there. So we've got lead going from +2 to 0. We've got oxygen. If it's gaining electrons. And then we've got oxygen, if we look, -2 and -2 is 4, and -4, so it doesn't really change. But the carbon goes from a +2 to a +4. So what's happened here? It's gained electrons. So it's oxidized. What's it done here?
Lost electrons.
Lost electrons. Gained electrons, so it's reduced, sorry. I'm wondering if you guys were looking at me. Lost electrons, so it's oxidized.
Question.
Yeah.
If you do, like, you said, with reducing is oxidized agent, and, with oxidized is, reduced agent. If you put that, would that be wrong? Because, I mean, it's very confusing, like you said.
It is confusing, and if you think about it as, okay, it's allowing the thing to happen. The agent the oxidizing agent allows somebody to be reduced. And the reducing agent allows somebody to be oxidized. That's the only way I can keep it straight in my head. It's the opposite of what it is. So this is your oxidizing agent. This is your reducing agent. Okay. So now, every for every carbon change, there's gonna be 2 lead. So how are we gonna balance this?
For lead, you're gonna put 2
In front of
lead,
here
yes.
and here?
over there. And for carbon, you're gonna put 4. Am I right?
Or can we just leave it the way it is, because it's the bigger of the 2?
Can we put
Isn't
2?
it already balanced?
It's already balanced.
It's already balanced.
Oh, wait a minute.
Which is why oxidation reduction is just kind of a pain in the ass, if you ask me.
Oh, geez, wouldn't that just mean it 3 oxygens on the other side?
Right. So if you looked at the original equation, it was already balanced.
0 and 0.
Mm-hmm.
So we don't need to balance.
So you didn't need to balance it. It was already balanced. All right. Let's try this one. All right. So if we've got iron oxide plus carbon, that's iron and CO2. So go assign the oxidation numbers. -2 plus 2, 0, 0, -4 plus 4. Are you okay with those? Although this oxygen's actually -2 to make 4. So if we've got a change in carbon from 0 to -2, or plus 4 rather, plus 4. And we've got a change in the iron from +2 to 0. Which one's oxidized?
Carbon.
Yeah,
Oxidation.
Oxidation is a loss of electrons.
so it'll be carbon.
So this is oxidized. And this is a gain in electrons, so this is reduced. Okay, and we've got a change of 4 here, and 2 here. And we divide each by the bigger change. Alright, so this we're going to multiply by 1, these we multiply by 2. By the bigger change. So we have to stick a 2 here, and a 2 here. Carbons we leave them alone, and that's balanced based on oxidation reduction.
So with oxidation reduction, are you always gonna have an oxygen? In
No.
your equation?
No. The first one I did, we didn't have any oxygen in it. Copper, the aluminum, the copper chloride, and the aluminum.
How did you know what to multiply the differences by?
Basically, you take your bigger number
Mm-hmm.
and divide each into it. So we had a change of 4,
Mm-hmm.
and we had a change of 2.
Okay.
So 4 divides into 4. We only
Oh,
multiply that one.
okay.
And 2 into 4, so we multiply those by 2.
Okay.
Try that one. Try another one and I'll quit torturing you for today. Alright, let's try. So in this case, oxygen we know is a -2 here. So this mercury's gotta be a +2. What about these?
0 and -4.
0 and 0. If it's by itself, it doesn't matter if it's monatomic or diatomic, it's still 0. Okay? So mercury, we're going from a +2 to a 0. Oxygen, we're going from a -2 to a 0. So this is a decrease in oxidation number, so it gained electrons. GER, Leo says GER, gaining electrons is reduced. So it's the oxidizing agent.
When I'm naming them, I look at this number, and if it's going from a larger number to a smaller number, then it's reducing the numbers. So that's how I remember.
Yeah.
Getting more negative.
Mm-hmm.
Because it's gaining electrons, because electrons are negative. This lost electrons. So it's oxidized. And it's the reducing agent. And in this case, as far as oxidation reduction goes, we had the same change, 2 and 2. So theoretically, everything should just have 1 by it. But we know that's not right as far as balancing. We're going to have to do this and this. So oxidation reduction can help balance in some things, but not in everything.
So why even use it?
Yeah, that's pretty much my theory. Why the hell do we use it? Okay. Questions? Al? Well, we'll get into the half reactions tomorrow. I think it's kind of a slow Monday for everybody, but